Okay, let's hope this recording goes smoothly. I meant to grade homework for you over weekend. Unfortunately, everything came up, so I was unable to, but I hope to get to that quite soon. Now, last time I discussed how you show that a one-step and then a multi-step method is consistent. Today we're going to see how to show that whether these methods are stable. So then if a method is consistent and stable, but you can conclude from there that it is convergent. And then I'll comment briefly on convergence as well if we're talking about stability. Now, I'm going to recall for you the definition of stability right here. That if you have a change in the initial data, then the change in the solution um, is bounded by a constant times the change in initial data. And what's very important is that the constant be independent of h. So at least that imposes some bound independent on how much a change in a solution. Sorry, how much a change in a solution. Uh, sorry, I cannot talk today. It imposes a bound on how much a change in the initial data changes the solution, and this is along the lines of one of the conditions for a problem being well posed. One of the conditions for a problem being well posed is that the solution depends continuously on the data. So we have the same um, concept here for the numerical solution. Okay, um, so as of a definition of consistency, this definition of stability is difficult to work with directly. Um, so we'd like to be able to have a faster way to check whether a one-step or multi-step method is stable. Um, okay, so for stability, uh, so problem y prime equals f of ty. So the original ODE we're trying to solve is well posed. Um, so solution depends continuously on the data. Um, if the function f is Lipschitz continuous, um, and the problem solution is that's two of the conditions of well-posedness, existence and uniqueness. But just the other third condition, depending continuously on the data, one way to ensure that is if you know that f is Lipschitz continuous um, in y, and the meaning of that is that we've seen this before. Just refreshing your memory: f of x minus f of t y1 minus f of t y2 is bounded by some constant L times y1 minus y2. So the change in f for two different y values, same t value, is bounded by a constant times the change in the y's. Um, so that's for the underlying problem. What about the numerical method used to solve this problem? We actually want a similar condition for that. Um, so um, so this goes under stability for one-step methods, where I need this Lipschitz condition. So similarly, a general one-step method that has this form: yn plus 1 plus yn plus h, some function phi of dn yn plus 1, if the case is implicit, and h is stable if a function phi satisfies a Lipschitz condition, so it's Lipschitz continuous. So it's two different ways of saying the same thing. If in the yn and yn plus 1 variables. So just as we want f from the ODE to be Lipschitz continuous in y, phi should be Lipschitz continuous in those arguments that correspond to solution values, yn and yn plus 1. So then we have the following. So how we could write this out is, suppose we have two different, so given two initial conditions, or two initial values really, y0 and tilde y0, for the same ODE. So it's still the same f, just different initial values for the initial condition. Then we have the following. Okay, so the difference in yn plus 1 minus tilde y n plus 1. So that is less than or equal to, just plugging y0 and y0 tilde into the method, and we keep time stepping. So the difference in n plus 1 values minus the difference in n values, yn minus tilde yn plus h times the difference in phi values with yn versus yn tilde and yn plus 1 tilde, yn plus 1 versus yn plus 1 tilde. So what that's going to give us is, okay, phi tn yn plus 1 h minus phi tn tilde yn plus 1 h. Now, if phi is Lipschitz continuous in the in yn and yn plus 1, and I'll write out what that means. So we have is this expression right here. So that is less than or equal to some constant L1 times the difference in yns, plus another constant L2 times the difference in yn plus 1 values. So then, if I incorporate this up in here, then what we have is the difference in n plus 1 values is less than or equal to, so there's going to be some algebraic hocus pocus here, because I'm going to replace this with this right here. Now, with a difference in yn values, I have 1 plus hl1. And then for the difference in n plus 1 values, I have that over here, and I need to move this to the other side, so I can get 1 minus, for moving it to the other side, hl2. So then, after rearranging, and you can try this yourself, to verify, so 1 minus hl1, or sorry, 1 plus hl1 up top, and then 1 minus hl2 down below, and then I have yn minus tilde yn. So this is how the change in the solution at time n might be amplified to get the solution at time n plus 1. Okay, now let's see. Now what I'm going to do is, to simplify things a little bit, L phi equal the maximum of L1 and L2. Okay. Okay. All right. Actually, no, I'm not going to do that just yet. So I want to work on this fraction a little more. So because I can write this as, if I write the numerator as 1 minus HL2 plus HL2, then then what I have here is 1 plus 1 minus HL2 down below, and then I have HL1 plus L2. Okay, now one thing that's important about the definition of stability is that since we're interested in what's happening for sake of convergence, as h goes to 0. The method is convergent if the error goes to 0 as h goes to 0. So, all right. And notice here the definition of stability, we require only that h be sufficiently small. It doesn't have to cover all h, just h sufficiently small. So I'm going to make an assumption on h. We assume that 1 minus HL2 is positive. We certainly don't want division by 0 here. So we let H naught okay. All right, and I'm going to let this be equal to, or sorry, greater than or equal to some value delta that is positive. So if I choose H naught so that this is equal to delta, I'm going to let this be 1 minus delta over L2. All right, but so we assume we require the above, this to be satisfied for h less than or equal to h naught. Okay. So now, so because I want to have an expression here, and since I interrupted myself here, I still need that there. I want, all right. I want to try to simplify this, and eventually, when I apply this across all time steps, get something that is independent of h. There'll still be a dependence on h within one time step. Okay, so now, because 1 minus HL2 is greater or equal to delta, I can replace the denominator by delta. So now what I have up top is so I have 1 plus H L1 plus L2 all over delta. Okay, so now I have that. Okay, so now that I have the this expression, solution at time n plus 1, bounded by the difference in solutions at time n times this constant, if I go ahead and apply this across all time steps, now I have yn minus tilde yn is less than or equal to this constant raised to the n power times the difference in the initial data. Okay. But now what I can do with this is both these terms are positive. So if these are the first two terms in the Taylor series, the exponential, and because everything's positive exponent, it's a lower bound. So I can say e to the, so this is the exponent here. And then, so I have HL1 plus L2 over delta. And all of this is raised to the n power, so n gets folded into the exponent. Okay. But, sorry, that should be hn. Not sure where b came from. But what is hn? Because the total number of time steps is final time minus initial time divided by h. So h times number of time steps, that is less than or equal to final time minus initial time. So, so what we've shown here is we met the definition of stability. Here's the definition here. Solution at time n less than or equal to a constant k independent of h times difference in initial data. And here's a constant k, what we have here in the exponent. And it is indeed independent of h. So that's how this condition that if function 5 that defines the one-step method is Lipschitz continuous in the variables corresponding to the solution, what I've shown here is therefore it meets the definition of stability for a general method. So now, if we give it a one-step method, if we want to know if it's stable, we don't have to resort to this definition. We don't have to do any of this. We can just check this. So is the defining function phi Lipschitz continuous in these two variables? Okay. All right. So as an example, show that the midpoint method yn plus 1 plus yn plus hf of tn yn plus h over 2 f of t n y n is stable. So this requires that showing that t, y, h, which is equal to everything in here except for a factor of h. So it's going to be f of t and then y plus h over 2 f of t y is Lipschitz continuous in y. Now, this is an explicit method, so it doesn't depend on yn plus 1. So there's no need to show continuity in an argument that doesn't exist, because it's trivially true, just because the difference in values with respect to that variable, if it's not included, would be 0. Any change is accounted for in this variable. There'd be no change to account for over here. So like a Lipschitz constant of 0 would work in that case. So we'd have to focus on this one variable. So we assume that f has a Lipschitz constant of L. So what that means is here, f satisfies this condition with Lipschitz constant L. So we'll find out what the Lipschitz constant is for phi, and it'll be expressed in terms of this capital L. Okay. Usually when I get a call, recording cuts out, but it appears to be continuing. So what I'm going to do is to check Lipschitz continuity. I'm going to check if all right, so phi of t y2h minus phi t y1h. So all the other arguments are held fixed. It's only y that changes. So what does that equal to? So I have f of t y2 plus h over 2 f of t y2 minus f and I have ty1 plus h over 2 f of ty1. So I need to bound this in terms of the difference between the y values, y2 and y1. And I can do that using the Lipschitz continuity of f. Now I'm going to need to make this a multi-line equation real quick. Okay, so I have a Lipschitz continuity of f that is less than or equal to a constant L, a Lipschitz constant for f, times the difference in these two arguments. So what I would have is this argument for a first call to f minus the second argument of this usage of f. Okay. So now what I can do is a little algebra real quick. So I have L times y2 minus y1. So that's a part that's just due to f itself, plus h HL over 2 times f of t y2 minus f of t y1, but that is also bounded by L times y2 minus y1. So if I put everything together, so I have L plus HL squared over 2 y2 minus y1. And that is enough. Okay, so but we're actually done at this point. You can say phi is Lipschitz continuous in the y variable with Lipschitz constant L phi, which corresponds to L1 from before, and that's equal to Lipschitz constant for f, but we have this extra term added on due to the method. Okay. So now, really, we need this Lipschitz constant to be enforced when h is sufficiently small. So, so if I consider h to be bounded in some interval, so like h less than or equal to h naught, so that Lipschitz constant works for h less than or equal to h naught. So for h sufficiently small, we do have a Lipschitz constant. That is enough to meet the definition for stability, which also applies, which also requires only that h is sufficiently small. Okay, so for a general one-step method, you identify a function phi, and you perform manipulations like this, piggybacking off of the Lipschitz constant of f that we assume exists. Now, for an implicit method, you have a little more work to do in that you have difference of uh, values of yn and values of yn plus 1. So you would need to show something like this. Now, in the book, I actually have one Lipschitz constant. That's just taken to be the maximum of these two, L1 and L2. That's something you could do as well. That would simplify the computation a little bit. The point is, you're bounding it in terms of the difference in both arguments added together. Okay, so that's all it takes to show that a one-step method is stable. Work with a function phi, show its Lipschitz continuous in yn, as was done here, and also yn plus 1 if a method is implicit. And as was shown up here, by using that relationship and applying it repeatedly to show how the solution at time n depends on the initial data and how it changes. This is why we can obtain a growth constant that is, while it may depend on a time interval, it is still independent of h, and that's what really matters here for a stable method. Okay, so that's one-step methods. What about multi-step methods? So fortunately, there's a simple way to check that also. All right, so stability for multi-step methods. So let's put up a form of a general multi-step method, so I need to refer to it. So left side is a linear combination of y values, and then on the right side we have h times linear combination of f values, and we have constants alpha i's on the left side, and f values on the right side, betas on the right side. Okay. So what we do is we check if it is zero stable. So I'm going to flesh out the definition of zero stable for you. So it's supposed to be this very simple ODE. Y prime equals 0 and y of t naught equals y naught. So y is not changing at all since it has a zero derivative. So solution is just y of t is equal to y naught for all t. It's a constant. So if we apply the multitude method, then all we have is the left side. Equals 0. So this is a m plus 1 term recurrence relation. And a lot is known about recurrence relations and how their solutions behave. So we must ensure for stability that the solution of this recurrence relation does not grow with n. I ideally should produce the exact solution, a constant. Or at worst case, due to some inaccuracy, it may exhibit some decay, but certainly should not exhibit growth, or there's no way that it will meet the definition of stability for a general method. So we have to know something about how these recurrence relations are solved and what their solutions look like. So the characteristic equation that helps us solve it is obtained from the alphas. So we have is alpha 0, and then we have lambda to the m. So it's a polynomial equation. So what happens in this case is we get to roots of this characteristic equation. So there will be m of them because it's degree m, which may repeat or be complex. So then the solution of recurrence relation just spotted a typo in the notes. In the notes I have some going from 1, this is going from 0 to m. It should be from 1 to m because there are m roots. So I have constants that depend on the initial values, and then I have n to the pi to the n. So a solution of recurrence relation has this form where all the lambda values are the roots of the characteristic equation, and the pi are integers, so this accounts for repeated roots. So for example, if all roots are distinct, then all the pi's would be 0. If you have a root that occurs 3 times, then you'll have values of pi being 0, 1, and 2. All right. So to be more specific, pi is equal to 0, 1 up to mi, where mi is the multiplicity of root lambda I. So sorry, mi minus 1, rather. Nope, not there. Here. So that's why if all roots are distinct, if multiplicity 1, then pi can only be 0. All right, so we need to make sure that this solution does not exhibit exponential growth. So the roots must satisfy the root condition, which actually has two parts. So the first part is the roots cannot have absolute value or complex modulus that is greater than 1. It must be less than or equal to 1. If any of these have a modulus greater than 1, the solution will definitely grow with n. The other condition is if it is equal to 1 in absolute value, then it cannot be a repeated root, because if it's a repeated root, even though lambda I to the n won't lead to any growth in magnitude, say if it's a double root, you're going to have a factor of n in one of the terms, and that will lead to growth in the magnitude of yn. So, so by requiring that such roots be a simple root, then we're still okay. We won't have growth over time. If a root is less than 1 in magnitude, it can repeat. And we have these factors of n or n squared or whatever, but that is overcome by exponential decay, so it won't present a problem. So we say a multi-step method is zero stable if it satisfies the root condition. Actually, I can say that it's an if and only if thing. Now, I can go a little further. It is strongly zero stable if lambda equals 1 is the only root on the unit circle. In other words, a magnitude equal to 1. And if that's not the case, then we say it is weakly stable. Now, for one thing, I should mention that in order for method to be consistent, one has to be a root, because one of the conditions that we saw last time for consistency is that the sum of the alphas must be equal to 0. So suppose I plug in lambda equal 1 here. Then what I have on the left side is a sum of all the alphas. And since that must be 0, lambda equals 1 has to be a root. So we're always going to have at least one root on a unit circle. If it's the only such root, then we could say it's strongly stable. Now, some examples. So an Adams method. An Adams method, where it's Adams Bashforth for Adams Moulton, has a characteristic equation. Same equation for all Adams methods. Lambda to the m minus lambda n minus 1 is equal to 0. Because alpha 0 is always equal to 1. Alpha 1 is always equal to minus 1. So So I can factor out a lambda to the m minus 1 out of this, and I get lambda to the m minus 1 times lambda minus 1. So the roots are lambda equals 1 and lambda equals 0, repeated m minus 1 times. Because lambda to the m minus 1 is a factor in the characteristic equation, and the only remaining factor is lambda minus 1, appearing only once. So we only have one root that sits on the unit circle in the complex plane as lambda equals 1. Okay. Another example. Simpsons method. Yn plus 1 is equal to, where'd it go? So this is a rather unusual multi-step method. It is not an Adams method, because notice I have yn plus 1 equals yn minus 1 plus h over 3 fn plus 1 plus 4fn plus fn minus 1. Okay, and it's not a BDF either, because a BDF would only have one beta on its right side, a beta 0, but this has other beta values. So it's neither Adams nor BDF. Has the characteristic equation. So yn plus 1, alpha not equals 1. So that gives us a term lambda squared. And it's lambda squared because this is a two-step method. Notice we go back to time n minus 1. So it's, however far back you go, it indicates what the value of m is. So because we go back 2 steps, it's a two-step method. So the leading term of characteristic equation is lambda squared. And if we look at the general form of characteristic equation, alpha 1 is 0 in this case, and then alpha 2 is the constant term. And in this case, that would be equal to minus 1. So that's a characteristic equation in this case. So the roots are plus or minus 1. So it's weakly stable because there are 2 roots that have a magnitude of 1. I mentioned BDFs a little while ago. A BDF is 0 unstable. So we're talking about an m-step BDF method. 0 unstable for m greater than 6. So we end up having roots that are either outside the unit disk or have too much multiplicity sitting on a unit circle. So it just doesn't satisfy the conditions. Okay, so that's... Now, I haven't explained why, if a method is 0 stable, it meets the general definition of stability for a general time-stepping method. That is a lot more complicated to go into than it is for one-step methods, which actually took the time to show. There's a reference in the textbook, Isaacson and Keller. They use the theory of non-homogeneous recurrence relations to make that leap. So it's a highly non-trivial theoretical leap to show that if a multi-step method is 0 stable, then it meets the general definition of stability. Okay. Now, the last part for today is about convergence. But there's actually not much to there's really not a whole lot to say here. But here's what just because the basic idea is if a one-step or multi-step method is consistent and stable is convergent. Now for uh, a multi-step methods, it is I can make a slightly stronger statement. Okay. Is consistent, then it is convergent if and only if it is zero stable. So that gives a partial converse here. So consistency is so first that's a sufficient part. So given consistency, then convergence then zero stability is necessary and sufficient for convergence. And this is the Dahlquist equivalence theorem. So that's a slightly stronger statement than consistency and stability implies convergence, is because there's a little bit of a converse going on here. Okay, now for one-step methods, if phi has a Lipschitz constant L phi, meaning that phi of t y n plus 1 h minus phi t tilde yn tilde y plus 1 h less than or equal to L phi times the difference in y values and n plus 1 values. So basically L phi is a max of L1 and L2 from before. All right, so what we can say in that case, in going from basically similar manipulations to what I did before, and these were actually worked out in a book. Actually, I'm going to put this onto a new page here. Then n minus tilde yn is less than or equal to the difference in the initial data times, and so we have oh, okay. Sorry, I need to go back to my notes a little bit. So I have a exponential constant that's e2l phi t minus t naught over delta. Okay. So that's the stability part from before. Okay. All right. Although I actually need to backtrack a little bit from that. Okay. Actually, I want to make sure that I have this correct in my notes from earlier about the definition of, yes, of H naught. Okay. How the error all right. So what we have here is 1 minus okay. Sorry. 1 plus two HL phi over delta. All right. Now, if we go back to how convergence was originally shown quite some time ago for Euler's method, we had a similar relationship. If we let En equal to Yn minus Y of Tn. So Y of Tn, the exact solution value, is playing a part of the tilde values here. Sorry, that should be a Y tilde n plus 1. Okay. And if we go back to that proof, where we had a similar relationship between new error and old error. Okay. That was way back at the beginning of a chapter.